Hey guys, my name is Z and you're watching You Makes It Easy, and welcome to the IGCSE Chemistry series where today we have topic 5, which is Organic Chemistry. And for the lessons that I'll be covering are as follows: crude oil, separating crude oil, combustion of hydrocarbons, alkanes and alkenes, addition and substitution, cracking, isomer polymerization, properties of polymer, ethanol, carboxylic acid, esterification, and condensation polymers. So this will be, I guess, a huge and long video, and maybe it will be like an hour. So just sit back and check out the pinned comment for any timestamps. So we'll move on to our first one, which is basic facts. Like you can see the diatomic elements and monatomic elements and different facts about the periodic table. So for the first lesson we have crude oil, and we have some formulas first. Just here are the differences between molecular formula, empirical formula, general formula, structural formula, and display formula. And then we have hydrocarbon. So here are some facts. Here's a hydrocarbon. Each carbon forms 4 bonds, and there are 13 bonds here. And these are all covalent bonds because it's C and H, and each H has 1 bond. And the molecule is made out of non-metals, that's why it's a covalent bond. And the molecule only contains carbon and hydrogen because it's a hydrocarbon. The molecule has the molecular formula of C4H10. It has an empirical formula of C2H5. It is a molecule of butane, and it belongs to the family of molecules called alkanes, which we'll look into it later. So here's crude oil. Why is crude oil so useful? Because it can be used in different things like crude oil, it can make into alkenes and alkenes, fuel, oils, and polymer, and much more, and it's for chemistry. And here's 5 questions. How is crude oil formed? So crude oil is created through the heating and compression of organic materials over a long period of time. Oil is a fossil fuel that has been formed from a large amount of tiny plants and animals such as algae and zooplankton, and they fall to the bottom of the sea once they die and get trapped under multiple layers of sand and mud. So what are the different methods by which crude oil is obtained from the ground? The most common extraction method is drilling. Geologists will first identify a section of land they believe has oil flowing in it using satellite imagery, and then they will drill into the land to obtain crude oil. So which countries supply crude oil? And it's in order, it's in Saudi Arabia, Russia, Iraq, Canada, UAE, and these things. So these countries over here. And how long will supplies of crude oil last? Crude oil reserves are vanishing at a rate of more than 4 billion tons a year. So if we carry on as we are, our known oil deposits could run out in just over 53 years. So we have to switch to renewable energy like solar, electricity, or like tidal wind. Is crude oil the same from all parts of the world? Oil is not the same as around the world. It can be light or heavy based on its density. And crude oils that are lighter, or like highest in API gravity or lower in density, and sweet, like low sulfur content, are usually priced higher than heavy, sour crude oils. And Saudi Arabia has the best crude oil quality due to its geography location. So here's separating crude oil. We have to separate crude oil because crude oil is a mixture of comparatively volatile liquid hydrocarbons, and basically it's composed of mainly hydrogen and carbon, and it's made out of a lot of hydrocarbons, though it also contains some nitrogen, sulfur, and oxygen. So here's a crude oil fractional distillation. We have crude oil going into the fractional distillation, this column right here, and then heat will go up and the thing will evaporate, which we'll look into it later. And here's distilling crude oil. And we'll move on to more oil refinery. The oldest and most common way to separate things into various components, called fractions, is to do it using the differences in boiling temperature. The process is called fractional distillation, and you basically heat the crude oil up and let it vaporize and then condense the vapor. Newer techniques use chemical processing on some of the fractions to make others in a process called conversion. And you can have a read for the oil refinery. And then we have fractional distillation. And this thing over here was similar to the one just now, and it's called a fractionating column. And it separates the different chemicals in crude oil. and fractional distillation works for substances that have the similar boiling point. Like, let's say we have ethanol and water because they have the similar boiling points, 79 degrees Celsius and 100 degrees Celsius. So when it reaches 79 degrees Celsius, the ethanol boils off, and some water may also have enough energy so it evaporates. And as the gas they evaporate, it goes to the fractionating column over here. And the water particles, because they don't have much energy left, they condense. So they condense on the side and it falls back down to the flask. But ethanol continues diffusing up to the tube and the condenser over here. So it just goes here. And here they run water in, water out. And then ethanol will condense back to liquid form or aqueous form, and therefore condensing back to the receiving flask. So here we have different fractions. So here's an oil refinery. We have the fractionating column. We have bitumen, fuel oil, diesel, kerosene, and petrol, and it's decreased in size of molecules. So here's more on the separating crude oil for gasoline, kerosene, and diesel. Here we have darker going to diesel, boiling point increases and viscosity increases. And viscosity is basically talking about how easily a substance can flow. And bigger molecules, bigger intermolecular forces of attraction, more difficult to break these bonds, and higher boiling point and more viscous. So like viscous is like thicker and more gloopy. So move on to crude oil fractional distillation. As you can see, you can have a read of all the information over here for how you can separate crude oil. And here's the boiler, and here's the distillation column. So crude oil is pumped into the distillation column over here, and it will evaporate based on their boiling points, like the different hydrocarbons in the crude oil. So here's refinery gas, petrol, and these things. So move on to the table, where you can see like the first column, second column, which is top and the bottom, like refinery gas to like lubricating oil and paraffin wax. The boiling point, you can see there's a big difference, and the color, length of hydrocarbon, flammability, and viscosity. So the gasoline that we use for cars are it's quite light colored, and the length of its hydrocarbon isn't very long. And you can see the flammability, it's very flammable, and it's not that viscous because it has a low boiling point, so that's why it's not viscous. So we'll move on now to more questions. We can read question 1, 2, 3, 4, 5, 6, and some. And then we'll move on now to more questions, like from question 11 to question 19. Then we have combustion of hydrocarbons. We have burning versus combustion. So burning is setting something on fire, and it always creates a flame. And combustion is a chemical reaction that involves the oxidation of a fuel, and it may or may not create a flame. So then we have methane, like burning or combustion of methane. Methane or CH4 burnt in the Bunsen burner. And here's a video over here, which you can see this. I'll just play it while I answer the question. Why does the color of the flame change as you open or close the hole at the bottom? And because when you open the hole at the bottom, more oxygen and air gets into the Bunsen burner, making the flame blue. So it's hotter flame. And when the hole is closed, the flame is yellow. What is the formula of methane? It's CH4 because it's a hydrocarbon. And what are the two types of combustion? There's complete combustion and incomplete combustion, which we'll look into it later. And what are the products of these reactions? You can see here. Complete combustion for CO2, and CO and C are incomplete combustion. And what is the evidence that incomplete combustion has taken place? The evidence is the flame will be yellow. So we'll move on now to combustions. We have complete and incomplete, as we talked about just now. So for complete combustion, it's something plus O2 because combustion always needs O2, oxygen. It will always produce carbon dioxide and water. But for incomplete combustion, it will produce water as well as products like CO, like carbon monoxide or carbon. But it's typically carbon monoxide. Over here, the first one. So we'll move on now to more complete and incomplete. You can see in excess air and in limited air, you can have a read for the equations. And complete combustions happen in excess air where plenty of oxygen is available. And in incomplete combustion, it's in limited supply of air where there's limited oxygen. So we'll move on now to more abstract information. You can have a read. And if the fuel is highly unsaturated or aromatic, complete combustion is more difficult. And here's what it means. And then we move on to more abstract information. We have the diffusive flame, which is the yellow flame, and premixed flame, which is the blue flame. And then we'll move on to carbon monoxide. You can have a read for the information, like how we know that carbon monoxide is sometimes referred to as silent killer because it's very poisonous. And the most common symptoms. And carbon monoxide is difficult to detect because it has no smell, taste, or color. And then what causes carbon monoxide to leak? It is caused by incomplete combustion of fuel. So you can see, like blocked chimneys can prevent carbon monoxide from escaping. Like the risk of carbon monoxide poisoning can occur anytime in the house or in enclosed space. Then we move on now to more carbon monoxide questions. What are the symptoms of carbon monoxide poisoning? And it's due to it's like dizziness, vomiting, and stomach pain. Why is carbon monoxide dangerous? And it's because hemoglobin in the blood binds to carbon monoxide instead of oxygen due to hemoglobin having a greater affinity with carbon monoxide than with oxygen. So hemoglobin will bind with carbon monoxide. So by having a greater affinity, it means that the hemoglobin will just cling onto the carbon monoxide without letting it go. So it can't get released into, like, let's say bloodstream to be released out of the body. So it will just the hemoglobin will keep holding on to the carbon monoxide. So why is it poisonous? It's because your brain and your heart won't receive enough oxygen for aerobic respiration. And what causes it to build up? It could be due to blocked chimneys or closed car windows. And how can you detect carbon monoxide? And you can use it by installing a carbon monoxide alarm. And we'll move on now to more questions for carbon monoxide. You can have a read. And then we can see car engine. We have the intake, compression, ignition, and exhaust. And you can have a read. And we'll move on now to acid rain. And this acid rain, I covered it in my first lesson for chemistry, I'm pretty sure, the reactivity series. So go check the reactivity series chemistry video for more in-depth of acid rain. But we'll move on now to alkanes and alkenes, which is the exciting part of organic chemistry. So how many bonds can carbon make? It can make 4 bonds because it's 4 plus or 4 minus charge. So here's the table for alkane. We have the molecular formula and the name. And then we have saturated versus unsaturated. So here we have here we have alkane and alkene. Note that they both are made of only carbon and hydrogen because they are hydrocarbons, which are only made of carbon and hydrogen. And alkanes are saturated because it cannot accept more than any more H2 atoms, because there's no double bond and they're all saturated. You see single bonds, means you can't just replace one or just add one. And alkenes are unsaturated due to double bonds present here in the carbon. So you can just add, you can remove the double bonds and add like an atom or any element here. But the double bonds can be broken to fit H2. So then we have homologous. Each series has a general formula, and all members possess the same functional group, and it is a functional group that gives the series its characteristic reactions. And there's a gradual change in physical properties from one member to the next, like increasing melting and boiling points as we go up a series. The reason for this is that molecules get larger and therefore harder to break apart. Can you suggest why? And it's because members of the same homologous series have similar chemical properties. And homologous series is a sequence of compounds with the same functional group and similar chemical properties. Then we'll move on to homologous and functional group. You can have a read. It's basically what I said just now. And here's the naming for alkenes. We have MEPB for the first 4. Monkeys eat peanut butter, or any other acronyms. So M stands for me something like methane or methane, ethane or ethene, propane or propene, or butane or butene. You can see the formulas. Then we'll move on now to some general formulas. For alkanes, it's Cn and H2n plus 2. So let's say C3 H23 plus 2, which is 8. So it will be C3H8. And for alkenes, we'll focus on the one on the left only, or the alkene. Is Cn and H2n, which is relatively simple to memorize. And as I talked about just now, the acronym MEPB and PHHO. And the acronym like math, F, prop, but, pen, hex, hep, and oct, for respectively 1 carbon, 2 carbons, and these carbons. So if it's 1 carbon only, it will be C1 H21 plus 2. So it will be C1 and H4. So C1 and H4, we know that it's an alkane and 1 carbon. So 1 carbon over here, meth, it will be methane. But if it's here, if it's C1 and H21, which is C1 and H2, and it's an alkene, it will be methane. So you can see the difference there. Then we'll move on now to more alkanes and alkenes. Where now we will focus on alkanes. You can see the molecular formula, name, the model or displayed formula, condensed structural formula, and the general formula, which is CnH2n plus 2, as we talked about in the previous slide. And then there's alkenes, which is up to butene. Then we'll move on now to the differences and the similarities between alkanes and alkenes. So you can see saturated, unsaturated, hydrocarbons, and boiling point increases as size of the molecule increases. And then we have addition versus substitution, and we'll focus on addition, which is for alkene. And when you add H2 or any element or compounds to an unsaturated alkene, it's called addition reaction. And the reason why it can happen to alkene but not alkane is because alkene, as I talked about just now, have double bonds. So the double bonds can be broken and you can fit or react with any elements or compounds. But alkanes, there's no double bonds and it only contains single bonds, so you can't react or add any elements or compounds. So here you can see an alkene plus bromine equals 1 to dibromomethane, so dibromoethane. And here, so here's another reaction: ethene plus hydrogen equals ethane, ethene plus water equals ethanol. So move on now to substitution, which is for alkane, and it's when the hydrogen in alkane is substituted by an element. So let's say propene, and here, and this is an example for the propene, which is the one just now. But here we have then reactions for alkane substitution, like methane to chloromethane, here, and here. So we have addition versus substitution for free radical substitution, which is part of the substitution reaction for alkane. So let's say here we have a methane and chlorine is a gas, a halogen gas. So when UV light is passed through chlorine diatomic molecules, it breaks the diatomic bonds, so it becomes 2 chlorine ion, and as they share electrons, they become like an ion. And then for the propagation step, they react with the CH4, the methane, to form HCl and minus CH3 for 1 minus charge. Then that CH3 1 minus charge will react with a chlorine gas. Then this step keeps repeating, and this process is called chlorination. And termination is when the reaction ends. It can either be Cl minus plus Cl minus equals chlorine gas, Cl minus plus minus CH3 equals this, and these two together to make this. And as you can realize, you can see this, it has 2 carbons, which is ethane. Then we'll move on to cracking. So here's an example of cracking. It's octane to pentane plus propene. So cracking will always be alkane to alkane plus alkene. And cracking is breaking long saturated alkane chain into alkane plus alkene, because short chain hydrocarbons are more in demand and it's used as a fuel like gasoline. Then we'll move on more to cracking. Crude oil is separated into several different fractions using fractional distillation, and this separates hydrocarbon molecules by their size. and small molecules have lower boiling points and are collected nearer to the top of the fractionating column, and these small hydrocarbons make excellent fuels. Large hydrocarbon molecules have higher boiling points and are collected nearer to the bottom of the fractionating column. These are yet less useful because they do not burn very well, as they are not that flammable, and they do not make good fuels. So cracking is a process to use to break these large hydrocarbons down into smaller molecules so that we can use them as a fuel. Let's see cracking over here. Then we have more cracking. You can see long chain alkane into shorter chain alkane and alkene, heating and an aluminum oxide as catalyst. So you can have a read. So we'll move on now to catalytic versus thermal cracking. Catalytic cracking is when breaking long saturated alkane to use for alkene and alkene with a chemical reactor called catalytic cracker. And thermal cracking is breaking long saturated alkane to use for alkane and alkene from high temperatures to break the bonds. So you can see here. But we'll focus on the catalytic cracking. So we'll move on now to cracking experiment. You can have a read of how we conduct cracking experiment in the laboratory, or any, like, let's say in your chemistry lab or anything. You can see, like, placing cotton wool with add liquid paraffin, add a catalyst which is porous pot, zeolite or hydrated aluminum silicate into the test tube. Place the test tube horizontally with a clamp, put a bunk on it, and you can have a read, like heat the catalyst, and this and this. And note the last step over here, step 7. You have to, when everything is done, you have to take the delivery tube out of the water first before turning off the flame due to this condition called suck back. So be careful of suck back because gases expand when they heat it, and when you take the heat away, the gas contract. So you have to take it out first, or else the gas will contract due to a cooler temperature. And if you just take this flame off, and this will become a low pressure zone, and here become a high pressure. So the water from this part will suck into this test tube over here and might explode this. And then we have potassium manganate, like 7, KMnO4. And potassium manganate is a purple solution, and when it's acidic, it's a purple solution turns to colorless. And when it's alkaline, the purple solution turns to dark green, then dark brown. Then we have bromine water, and bromine water can be used to determine if the solution is an alkane or alkene. And bromine water is a brown-orange solution, and when it's an alkane, there's no change as the brown water remains brown-orange, because as we know, alkanes are saturated. And in alkene, it's from brown-orange and it turns into colorless, because the alkene can react with the bromine from the bromine water. So move on now to more bromine water information, like ethene plus Br2. You can see 1,2-dibromoethane, propene, 1,2-dibromopropane. So we'll move on now to isomer. Isomers are compounds with the same formula but a different arrangement of atoms in the molecule and different properties. Like you can see pentane. Here's an isomer of pentane. You can see it has 5 carbons and this has 5 carbons. But this longest chain is 4 carbons. I see the longest chain here is 5 carbons, like 1, 2, 3, 4, 5. But this chain 1, 2, 3, 4. Because the longest chain, if you go up this way, it will be 1, 2, 3, and 4. It can't be 5, so it's an isomer of pentane. And here, this is not an, let's say this is butane, right, because it has 4 carbons. It's not an isomer of butane because it has like the longest one is 4, so it's still considered a straight line. And then we'll look into isomerism. Isomerism is the existence of molecules that have the same numbers of the same kind of atoms but differ in chemical and physical properties. So you can have a read for isomerism and butane and propanol. So we'll move on now to isomers of heptane. We have heptane over here, 3, 4, 5, 6, 7 carbons. Then different things, different isomers. So here's how you name the isomer. So you count from the right to the left, right? So whenever it branches out, the carbon branches out to another carbon, we call it like 1, 2, the second one over here, and here's another third one. So 2 and 3 branches out, so and it only has one carbon, so one carbon is called meth, so it will be methyl. And then the longest chain has 1, 2, 3, 4, 5, 5 which is pentane, because 5 is pen. So this the name of this isomer will be 2, 3 di between 2, 2, 3 dimethyl pentane, the longest chain. And this 3, 3 and 2 methyl, so 3, 3 methyl pentane. And you can just figure out the others. And then we'll move on to addition polymerization. A polymer is a large molecule or macromolecule composed of many repeated subunits which are called monomer. And monomer are units you can add together to form polymer, and it's usually an alkene. And polymerization is, in chemistry, it's called the process of reacting monomer molecules together in a chemical reaction to form polymer chains or three-dimensional networks. And then we'll move on to addition polymerization. You can see some some monomers, and what the name of it, the structure, the diagram of the part, the polymer name and common name, and the users. Like it's a simple way to name it because, like I say, ethene, the polymer name will be polyethene. Propene, the polymer name will be called polypropene, and like chloroethene, it will be polychloroethene or PVC. Tetrafluoroethane, polytetrafluoroethane, or Teflon, or the non-stick pan, and you can have a read. And we'll move on now to more drawing diagrams. Like here we have ethene, a monomer of ethene, and when you're trying to draw it to polyethene, you have to break this double bond over here and make it a straight line and put 2 lines across. And if it's only one repeating subunit, you have to put a bracket over and put N. N standing for one repeating unit. And if it's 2N, then it has to be 2 carbons. And all polymers only have 2 carbons over here. Like as you can see this now, it's all only 2. But these, the 4 that branches out can have anything, like I say HHH. And here you have more than one C and more than one H. So, but the main thing to note is that it has to have 2 carbons on the main branch only. So we'll move on to properties of polymer. So you can have to see the reaction conditions. Temperature, pressure, and catalyst affect the length and shape of the polymer chain. The type of monomer, the type of molecules which used to affect the polymer chains. And additives is these can join together polymer chains with weak or strong crosslinks, which they are called, which we'll look into it later, but we'll focus on the biodegradability now. Biodegradable means an object can be decomposed by bacteria or microorganisms over a long period of time. And addition polymers are polyalkenes, and these molecules are saturated, as all of the bonds hold the carbon chains together are single bonded. So you can have a read for the biodegradability and condensation polymers and different polymers. So move on now to more biodegradability. You can see the name, polyethene, polyethanol, polypropene, its properties and its uses. And we'll move on now to properties of polymer. So why are polymers unreactive? Addition polymers like polyalkenes, and these molecules are saturated as all of the bonds holding the carbon chain together are single bonded. This makes them generally unreactive and chemically inert. And thermosetting polymers have cross links between polymer and sulfur, so the polymer is tough and hard to break apart, which we'll focus on later. And how does the nature of the intermolecular forces between chains influence a plastic ability to recycle? The greater the intermolecular forces between molecules, the higher the melting point and boiling temperature. So it's difficult to melt them and recycle them into new product. So what are the 2 types of plastic? They are thermal softening and thermal setting. And how has the production and properties of polymers changed over time? Polymers are designed to be more easily decomposed and manufactured. So here's more on drawing polymer. We have this, as we talked about just now. We have polypropene, only 2 carbons in the main branch, so it's HHH and CH3. polychloroethene only needs 2 carbons on the main branch, so it's CC, HHHCl, and put an N for how many repeated units. And polytetrafluoroethene, CCFHFF, and N for 1 repeating unit. And then we'll move on to thermal softening and thermal setting. Thermal softening, they have intramolecular forces between change, and they soften when heated and can be molded into different shapes. So boiling point uses an example and its structure. Because the polymers are not linked together so that they can slide over each other, just like how graphite works. And thermal setting, they do not soften when heated because the polymers are cross-linked using sulfur or disulfide produced, and it hardens the overall structure. And here's the boiling point uses an example. And then we'll move on now to more thermal softening and thermal setting. You can see we can classify polymers by looking at what happens when we heat them. And then we have ethanol. So here's the process, the two processes of ethanol. We have carbon dioxide to this. It's called the fermentation reaction over here. And here we have the hydration reaction. And ethanol can be made by two processes: ethene reacting with steam under pressure in the presence of a catalyst, or the fermentation of sugar using enzymes and yeast. And here are the equations you can see. Which brings us to our next slide, which is introducing ethanol via steam by hydration or fermentation. So here we have hydration or via steam. Heat ethene with steam in the presence of concentration phosphoric 5 acid as a catalyst in 300 degrees Celsius and 60 atmospheric pressure, or ATM, to ethanol. And this you can see a displayed formula. And this is an example of addition reaction similar to Br2 is added across a C double bond. And if oxygen is present in fermentation, the ethanol will turn into ethanoic acid. So it's important to keep it to have no oxygen. So here's the brewing industry. We have fermentation. So sugar equals ethanol plus carbon dioxide. Let's see. So the conditions are yeast needs to be available due to, because yeast is a biological catalyst, and the enzyme has to be in 37 degrees Celsius like body temperature, because the yeast optimum temperature is 37 degrees Celsius, and also be in the absence of air to prevent oxidation of the acid, as the wine or the ethanol will go sour. And here are the observations and thereafter. And then we have ethanol to ethene, which is the reverse process via dehydration. You can see from the ethanol, you can add concentration sulfuric acid with a temperature of 160 to 170 degrees Celsius to ethene plus water. So dehydration is ethanol to ethene, and hydration is ethene to ethanol. So move on to ethanol. Ethanol is a biofuel, and plants that are high in sugar can be used to make ethanol, like sugarcane or pineapple. And ferment the glucose using yeast, and yeast acts like a catalyst. And hydration of ethene, as talked about just now, uses phosphoric acid as catalyst. So here are the benefits of hydration. There's no byproducts because it's 100% atom economy. And atom economy is how much a product that's produced that is desirable. When an atom economy is 100%, it means that all the product that is produced is what you need. And fermentation benefits is that the reactants are renewable, relatively low temperature of 37 degrees Celsius to conduct, as optimum temperature of yeast is around 35 to 40 degrees Celsius. And if it's too high, the enzymes or the yeast will denature. Not kill, denature. Then we'll move on to oxidize. We have different ways ethanol can be oxidized. We have complete combustion with O2, microbial oxidation, that reacts with oxygen in the air to form ethanoic acid or vinegar, or potassium dichromate or VI in dilute sulfuric acid. You can have a read. So move on to alcohol. We have methanol, ethanol, propanol, butanol, because ethanol is one of the alcohol groups. It belongs here, C2H5OH. Sorry. And then here's ethanol, the summary. Ethanol is made out by one of two methods, hydration or fermentation. In hydration, ethene is reacted with steam in the presence of a catalyst, and this is a continuous process, so it is quick and produces pure product. And the ethene required is produced by cracking of large hydrocarbons, so this method is non-renewable as it requires crude oil. And in fermentation, the ethanol is prepared by the action of a yeast on sugar or glucose from plants with high sugar like sugar canes or potatoes or pineapples. And the yeast contains enzymes which catalyze the reaction, and it is a batch process, so it is quick and produces a pure product. And the sugar comes from the animal, so it is a renewable source of ethane. So then we have carboxylic acid. Here's the general formula. You have the CnH2n plus 1 COOH, or the formula for this is CH3COOH, which is ethanolic acid because there's 2 carbons. So ethane 2 carbons. Homologous series, carboxylic acid, and the functional group is COOH. Let's see, C double bond OH. So now we have homologous series for carboxylic acid. We have alkanes, these things, general formula. For IGCSE, it's just alkanes, alkenes, and alcohols, and carboxylic acid. But those are other knowledge to know, like this fluorocarbon and these things. So we'll move on now to homologous series for carboxylic acid as a recap again. Here's a fun fact. Vinegars contain water and ethanolic acid, and just know this. And carboxylic acid, CnH2n plus 1 COOH and COOH. So for the ethanolic acid, as I talked about just now, the formula is CH3COOH. Right here. So we'll move on now to carboxylic acid to draw. Here's a task to draw potassium ethanoate, which is potassium acetate, the same name, but the same thing but different name. And it's normal to draw this part like the covalent bond part, but this part O and K, oxygen and potassium, they are ionic bonded because it's non-metal and metal. So you have to write it like this: a minus and a plus. So move on now to the functional group. You can have a read the functional group OH, COOH, and COOH, and different acids for carboxylic acid. So move on now to carboxylic acid again. We have the different formulas. We have methanolic acid up until octanoic acid, which has, as you can see, 8 carbons. So here are the rules for organic chemistry as I talked about in the first slide. Then we'll move on now to carboxylic acid plus metal or metal carbonate. We have plus acid plus metal equals salt plus hydrogen over here. And acid plus metal carbonate equals salt plus water plus carbon dioxide for carboxylic acid. So we'll move on now to carboxylic acid functional groups. You have alkenes, alcohols, carboxylic acid, and esters. And we'll focus on esters in a minute, the functional groups, and the different displayed formula. Then we move on to esterification or making esters. So here's the formula for this one right here. We have C2H5COOCH3, which is methyl propanoate, and general formula is CnH2n plus 1 COOCmH2n plus 1, and its homologous series of esters, and its functional group is COO. And here's what esters are. Esters are volatile compounds, so it means they vaporize easily, and they are used in products like perfume because they vaporize easily, and food flavoring. And esters are made by reacting alcohol with carboxylic acid to form esters. So here's how to make esters. So we have this carboxylic acid over here. This part will get chopped off, and alcohol, this part will get chopped off. You can either put the alcohol chop off the H or the OH, or this chop off the H or this chop off the OH. So let's say in this case the OH will get chopped off in the carboxylic acid, and alcohol will be H cut off. So after through the acid catalyst, it will be this carboxylic acid over here, and this HO or OH over here, which is connected to this part, and water. And the part that connects to O is the alcohol, and while naming the esters, the alcohol comes first, So let's say here, alcohol plus carboxylic acid through heat and acid catalyst will be alcohol YL and carboxylic ATE and plus water. Now let's say we have methanol plus ethanoic acid equals methyl ethanoate and water. And then we have more on esterification. You can have a read for the diagram. An ester is formed when an alcohol is warmly reacted with a carboxylic acid in the presence of an acid catalyst and its sulfuric acid, and this reaction is known as esterification. Then here's more on making esters. You can have a read for the experiment. And what is the purpose of sodium carbonates? And they are there to neutralize the excess H2SO4 acid catalyst. And why do the layers separate? And it's because esters and salt and water have different density. And how could we separate the layers? And we could use a pipette suck the top layers out, or to obtain the bottom layer, or to obtain the top layer if you want. So we'll move on now to condensation polymers. And addition polymerization is made from one type of monomer, and the monomer is alkene. And condensation polymerization is the condensation polymer plus a small molecule, and this is what it produces. And condensation polymerization, it reacts two different small monomers to get a condensation polymer and another small molecule, which we'll look into it later. And like for example, react carboxylic acid with alcohol non-stop until a polyester is produced. And just now we know that carboxylic acid react with alcohol will become ester. So keep reacting it non-stop will become polyester, which you can recognize with the material polyester. And for condensation polymers to take place, the carboxylic acid and the alcohol have to have two different functional, two ends of the same thing. Like for alcohol, we call this diol, because OH. So one thing to note is that it's the wording of the OH on here. Because O makes two bonds, it has to be beside carbon so that it can connect carbon with hydrogen. If you read it the other way around, it will be hydrogen making two bonds, which is incorrect. So it's HO and this and OH. And dicarboxylate, like with COOH and C double bond O, OH. And this dicarboxylate and diol will react continuously. As in two different monomers which react with reactive ends. We call the diol or dicarboxylate reactive ends. And you can see this. Polymers containing alternating units, like esters, just keep repeating, like this. Plus a dicarboxylic acid and a diol to form condensation polymerization. And this process will have water, H2O. And then this whole chain is called a polyester. And here's how to draw polyester. And one thing to note is that the key term is ester linkage. So we have monomer A, we can see it's a diol plus OH plus OH. Then we have COOH, it's a dicarboxylate. So just keep plus. And we, for the dicarboxylic acid, we can just donate the OH to become become water. So the dicarboxylic acid will lose its OH, and the ethanol or the alcohol will lose its H. So the O will join to the C. So you can see C join to the O. So basically you ignore this part, you delete this part, you delete this part, you delete the H, and to form this. And if you decide to delete the H from the dicarboxylic acid and delete the OH from the alcohol, you have to make sure that the ends are the same. So like if you delete the OH from the alcohol, this alcohol can't have an O, because remember the OH is deleted from the alcohol. But depends how you write it. And if you still don't understand, just comment down below and I'll email you some things or some videos for you to understand, because it's quite a complicated thing. And polyester, plus, most importantly, plus n number of H2O. So that's it for my IGCSE chemistry series for a long video for organic chemistry. And I'm not sure how long this video will be, but I'm sure you guys have enjoyed this. And if you did, please leave a like and subscribe, and comment down below if you have any questions or criticisms. And just email me from my YouTube channel, the bio over there. You can check out my email, if you have any questions, just email me or just drop a comment. And I hope you guys have enjoyed this, and just follow my Instagram in the description for more daily content. And I hope you guys have enjoyed this, and I'll see you guys in my next lesson. Until then, stay safe and happy learning.